So yes, hello everyone. In today's class, we're going to start with the SN2 mechanism. So let's continue with this SN2 mechanism there. So let's see that what is so special about the SN2 mechanism there. So let's try to find out the answer. What is SN2 mechanism? So let's like the previous one. Let's decode this word that SN2 mechanism there. So what is SN2 mechanism? Same as for substitution. S for substitution, N for nucleophile, you can say nucleophilic, and 2 for second order. So definitely it is going to be the second order. As you observe in the SN1 mechanism, we discuss about S for substitution, N for nucleophile, and 1 for the first order. So it is going to be the second order reaction, SN2 mechanism. Okay, I hope the word is clear for everyone. What is the meaning of this word SN2 mechanism? Now, like what is difference here? Like what why the reason is what it's known as a SN2 mechanism. So first of all, let's just discuss about a general reaction. How about the general reaction there? So basically, let's suppose I'm having some Rx there, okay, and let's suppose we are adding some kind of nucleophile. So how we are end up there that this living group leave and we are end up with, let's say, this nucleophile attack this side. Did you notice something? What is happening there? That our living group is moving leaving the substituent from the front side, and now our nucleophile attack from the back side there. So in this case, what is the key point? If you're moving from there to there, okay, if you are moving from there to there, what is happening? There is an inversion of configuration take place. We will cover what is the meaning of this word inversion of configuration. So inversion of configuration take place there, okay. So that's it, this is very simple there. Now how about the mechanism and all these thing here? So let's just discuss about the mechanism of the SN2 reaction there. So how about the mechanism there? This mechanism is very simple. It follow only one step. It's not like the SN2 mechanism. It's a simple it's a single step reaction. One step have to be there. So how about the reaction there? First of all, we are having some Rx, okay. Let's just consider this is some C like this, and this is our living group connected. Okay, let's just consider the living group is going to be the halogen, because right now we are familiar halogen is a very good living group, okay. And this is some nucleophile there. So let's suppose this is my nucleophile there. So what is happening? This nucleophile basically attack here. Okay, so how about the case that this nucleophile start forming a bond, and living groups start living. So there is a condition occur. Okay, this is just for assumption only. This is just for a very small time. It's not like that is first of all nucleophile attack the living group leave. No, it's not like that. Okay, just wait. अम्मी क्या कर रही हो? Okay, so I'm sorry for this. Let's continue. Okay, so what is happening there? This is my nucleophile. This attack here. So let's see how the processor look like. First of all, this is my nucleophile, and this nucleophile attack from there, and this living group going to live. Now in between, we are end up with a transition state, okay? So this is its look like, and let's just use a different color, okay? So this living group start living, and this nucleophile start attacking. This is a known as a transition state. This is known as a transition state. Okay, so basically what is happening in a transition state, you can say the bond between living group and this carbon start weaken, and the nucleophile start forming a bond with the carbon there. Okay, so this is how the reaction is going on. And how about the next step? Now living group leave, and basically we are end up with only the nucleophile. Okay, so this is the simple mechanism here. It's a single step reaction, it's a one step reaction. Don't say ma'am intermediate form. No, it's not a intermediate, it's a transition state. If you to compare the lifetime of a transition state with an intermediate, it is very small basically. Okay, that intermediate takes some time, but this transition state not taking so much time here. Okay, maybe it's not very clearly visible to you. Okay, I guess now it's visible. Okay, so this is how the mechanism look like, very simple. And this is one of the famous one, maybe you already know about this, that is this is known as a Walden inversion. Okay, this is one of the famous, this is known as a Walden inversion. It's a Walden inversion. Now the question be like, why this is known as a Walden inversion? Like what is the meaning of this word invert? Maybe you are getting a little bit idea about this. What is happening? Living group living from the front side and nucleophile attack from the back. It means there's an inversion of configuration take place. Yes. Let's see how about the inversion of the configuration there. Okay, so let's try to answer, find out the answer for this question there. So let's continue further. Let's just move this. So, for example, let's just consider a simple example here. Okay, let's just consider an example. What if let's see, I'm having a carbon. This is connected with hydrogen and one more hydrogen and one more hydrogen, let's say. And this is how our X group is connected, let's say. Okay, and let's see, this is at the wedge position. Let's see some group so that we can find out the configuration, right? This is my CH3 and this is my CH2 and CH3. Can you just tell me what is the configuration for this? Options are S or R. Yes, please try to find out the answer for this question. Okay, let's just consider this is chlorine, okay? Chlorine, let's say. So is it R or S? R, okay. R, okay. R. Okay, so everyone is right. So it's going to be the R. But let's see. If you don't know, if you not attend the previous class, let me just explain how. So priority wise, the chlorine got the first priority, then this one the second priority, then this one the third priority there. If you to rotate so we are getting this kind of direction. So what is this? It's a clockwise direction. If you to observe this, this is my clockwise direction. If this is my clockwise, so it's going to be the R. Simple. R is there. Okay, cool then. Now let's see what is happening after once the nucleophile attack here. So let's see, this is the nucleophile. So basically what is happening, this nucleophile attacking from there, okay, like this, and this chlorine leave out, leave, okay. So how about the case what we're getting here? This is my carbon, and now see the observation here, this hydrogen at the wedge position now, okay, and if you to observe this nucleophile at the des position now, okay, now see this is a CH3 and the same this is a CH2 and CH3. If you want to find out the configuration, let me just use the nucleophile as a OH, okay? Just in order to understand the configuration, I'm doing this, okay? It's not like it can't be possible, okay? Yeah, I'm talking about a general one. But if let's suppose I have to switch this nucleophile file with some OH group there, OH, okay? So it means what we are getting simply, this is going to be my OH there. So it is going to be the OH and this is the CH2 and CH3 there basically. Okay, let's find out the answer for this part here. It is my one. Oh, sorry. I'm sorry for this. Okay, so this is one, this is two, and this is three there. So about the case there, it is one, two, and three. This is how it's rotated. And what is it? It is S or is it R? Yeah. Okay, yes. Right? Yes, everyone, you're right. It is going to be the S there, right? So let's just see this, how it is going to be this. So basically it's moving like this direction. So how about the direction there? If you to observe the direction, this is my sorry, clockwise, it means R. But no, if you to observe something, this is at my wedge position. And you know when this is the case, you have to revert the configuration. So R become S. Okay, this is very simple. This is how we have to observe this. In short, R become S and what is it? Inversion of configuration. So that's why we used to say it is a Walden inversion. Walden is the name of a scientist and an inversion means SN2 mechanism follow the Walden inversion there. Okay, so this is all for the mechanism of the SN2. Any problem with the SN2 mechanism, please ask. I guess it's easy, right? Okay then. Now next one, that is how about the graph, okay? Graphical representation. So let's discuss about the graphical representation again. So in the previous class we discussed about these kind of graph, that is potential energy diagram. So this side we are having a potential energy, okay? And this side we are having a reaction coordinate. It's a reaction coordinate. Okay, So yes, in this case, it's a single step reaction, right? In this case, we are not going to follow any step, only it's a single step reaction simply. So let's just back here. How about the case? This is some reactant, okay? And reactant simply moving toward the product there. Okay, so this is a simple diagram for this one. It's a reactant and it's a product. Let's just generalize this. How about the case here? So first of all, we are having this simple. There is some X group connected here. And basically here we are getting that is X start living, okay, and nucleophile start attacking here like this, okay. And the last step is what? That is we are getting simply nucleophile connected here. This is known as a transition state, okay. This is known as a transition state. And for this one, the lifetime is very small. It's quickly form and quickly you can say convert into the product, not very stable there, because you already observe the activation energy is very high. If the energy is very high, obviously it's not going to be stable one. Okay, so that's it. This is all for the energy diagram or energy profile diagram for the SN2 mechanism there. Okay, now same. How about the factor affecting the SN2 mechanism? Okay, so let's discuss about the factor affecting there. Factor affecting SN2 mechanism. Okay, before moving toward this point, let's just discuss about a very much important point, rate of a reaction, right? So, can you just tell me the rate of a reaction? Anyone if you know? Who's this Aaron Yeager? Yes, please. Okay. So now second one, that why this is equal to the rate is equal to uh, the K is equal to. So let's see how about the rate here. So let's just discuss about the rate. So rate, you know, rate is depend upon the concentration of the reactant rate raised with the some power, okay, which is experimentally determined, not the stoichiometric coefficient. So in this case, look at this. If you have to observe the reactant, this is my reactant number one, and this is my reactant number two. So I can say the rate is depend upon the nucleophile, right? And rate is also depend upon the reactant. So rate is depend upon two things. One is reactant, one is a nucleophile. So total how about the rate? 1 plus 1. So it's become 2. 2 is the order of a reaction. In short, this is a second order reaction. I hope now you're able to understand why the mechanism known as SN2 mechanism simply. Okay, this is all for the SN2 mechanism. It's a second order reaction. So now let's just back again here. How about the factor affecting? So first of all, in this case, if we are talking about the substrate, so this time the rule is very opposite. That is the primary react first, then secondary react first, then tertiary react first. Now the question will be like why? First of all, in this case, the rate determining step is not the formation of carbocation. So, okay, sorted. But why primary first? So let me just give you a kind of explanation for this one. This is a question for you. I'm having this is my carbon, and let's say two CH3 group is connected. Okay, like this. And one is hydrogen, one is this living group. Let's say living group. Okay, and here nucleophile is going to attack. Condition number two. This is A. Okay, and there is a some B. This is my carbon, hydrogen, and this is hydrogen, hydrogen, and hydrogen. And this is some CH, CH, CH. Wait. Okay, let's see one more. Only hydrogen have to be there, okay? Let's see only hydrogen. And this is my living group. So again, the nucleophile also attack here. So can you just tell me in which case it is easy for the nucleophile to attack condition number A or condition number B? B. B. Yes, you're right. But question be like why it is easy to attack in a B there? Because it's very simple. Nucleophile attack and this living group going to live. You know, there's a two thing is happening. One is leaving, one is entering. So think about it. If nucleophile attacking here, so there's a so much crowd, so much hindrance there. It's not like carbocation formation and SN1 mechanism that planarity and okay, they're in a one plane and nucleophile attack above the plane or below the plane. No, it's not like that. So it means that here we have to focus on the hindrance part. Of course, we have to focus on a hindrance part. So the rate of a reaction become opposite this time, primary, secondary, and tertiary, because it is very easy for the primary to attack in the reaction there. Okay, I hope this point is clear. Second one, that is this side we are requiring polar protic solvent. If we are talking about the solvent, okay, solvent. So here that is I hope you already remember in the previous one we are discussing what polar protic solvent, and there we have to follow polar aprotic solvent. What is the meaning of this word polar aprotic solvent? the solvent, which one basically does not have any kind of, okay, any kind of proton. For example, acetone. Acetone is the very famous example. In this case, it's not a proton donor. Okay, now my question to you, why it's not a proton donor? Because I'm observing some hydrogen have to be there, but why it's not a proton donor? Do you know the reason? Yes, please. Do you know the reason? Okay, what do you mean by this word proton donor? Okay, so a species or a molecule, no, it's not like that. Okay, so what is the meaning of the word? That is a proton donor. Okay, let's just compare with this. If I'm having this CH3 COH, okay, wait, OH. So in this case, what is happening? That if the proton remove, the oxygen achieve the negative charge. In this case, if let's suppose the proton remove from here, the carbon got the negative charge. So is this feasible? Carbon has a negative charge? No, because carbon is basically technically more electropositive in nature. So that's why the rule said that it's not really feasible. So carbon will be like, I'm not going to give my hydrogen to you. So that's why it's a polar abiotic solvent. It's one of the famous one, acetone. Yes, if you want to check is it SN1 or SN2 mechanism, always focus on a acetone. One more question for you. How about ammonia? Ammonia is a proton donor or not? Secondly, most of the time ammonia is also a solvent. Yes, please. Is it polar aprotic or protic? Aprotic. But isn't it the ammonia has a three proton? Then why? Okay, ammonia. Okay, if it is a proton donor, if it is a proton donor, so isn't it going to be the acid? But according to me, I guess ammonia is a base. Hmm? I guess ammonia is a base, right? And you already know ammonia is a base. If ammonia is a base, then what? Ammonia is going to take the proton. It's a base, right? It's not a proton donor. It is not a polar protic solvent. It's still a aprotic solvent. Okay, that's it. Most commonly used ammonia, and someone you can find out about this DMSO as well. So what is DMSO? That is dimethyl silane. So it is this is the case, that is D for di, M for methyl, and sulfoxide. So you can say that is D for di, M for methyl, dimethyl sulfur oxide. Okay, so that's it. This is the meaning of this word DMSO. Most commonly used DMSO as well, or acetone, most commonly used. That's it. This is all for the solvent. Let's see the third one. That is the same living group. How about the living group? That living group trend is very simple like the previous one. Iodine, then chlorine, then bromine, iodine, bromine, chlorine, and then fluorine. So these are the factor affecting the SN2 mechanism. Okay, first of all, any issue with this point SN1 and SN2? Let me just quickly brief. In the previous class, we discussed about SN1 mechanism. SN1 is a first order reaction, SN2 is a second order reaction. SN1 mechanism follow two step, but SN2 mechanism follow single step only. Okay, there is only one step. There is a formation of the intermediate, but in SN2 there is a transition state formation take place. In SN1 mechanism, we have to follow tertiary, secondary, and primary, and here we have to follow primary, secondary, and tertiary. Okay, so this is a common difference between both the cases. But now the next question, that how to identify. For example, if let's suppose I will give you a kind of option. Okay, this is a question for you. Just try to answer this. You know, don't know. Okay, can you just tell me in this question, the product formation follow the SN1 mechanism or SN2 mechanism? Yes, please. So, okay, let me tell you how to approach the organic chemistry questions, right? SN1, SN2. Okay, okay, okay. So, technically, just think about it. If it is follow the SN2 mechanism, right? So basically, what is happening there? This OH came into the picture, okay, and bromine going to leave, okay. This is simple SN2 mechanism. It means this is a single step reaction, okay. Condition number two, and it's not that much hindered. Phenyl is just a planar structure, so it's not going to interfere in this attack and nothing. Okay, condition number two. What if it does follow the SN1 mechanism, right? Let's just say it's follow the SN1 mechanism. So what we are getting, that is a carbocation formation. So isn't it the benzyl carbocation is the stable one? Yes. Then the interesting part start. So should we have to follow SN1 or SN2 mechanism, right? How to identify this? I just told you a point. Solvent. Yes, very good, Aditya. Ammonia is given to you. So it means the given thing is going to follow the SN2 mechanism, because sometimes tertiary, secondary, primary is not enough for us to identify all these things, right? So let's discuss about the difference between them. How to differentiate these things, that which one is stable and which one is not, okay? So let's see a kind of difference between them. Okay. So let's compare them. Comparison. First, let's compare them, and then I will tell you some kind of difference, important difference. It's a difference between SN1 and SN2 mechanism. Okay, so this side, let's just take this is SN1 mechanism, and this side, let's say it's a SN2 mechanism. So the difference number one, it's a unimolecular. Okay, I hope you know why this is a unimolecular, because it's only depend upon the concentration of substrate or reactant, you can say. On the other hand, it is a bimolecular. Okay, that's why it's a 2 and so 1 here, bimolecular. Because sometimes it's written like substitution, nucleophilic substitution, unimolecular reaction. Okay, next one, it occur in two step. Basically, it's follow the two step, but it's a single step, occur via single step. It's a single step reaction. Okay, next one, in this case, intermediate form. Intermediate is formed, and in this case, no intermediate form. Okay, so these are the three differences. Let's just move further. Okay, like the same, this side SN1 and that side SN2. So next one, that is alkyl halide follow. Alkyl halide follow the order tertiary, secondary, and primary. And on other hand, in this side we have to follow primary, secondary, and tertiary. And here we are requiring that is polar protic solvent. And this side polar aprotic solvent. Okay, this side partial racemization. I hope you remember the racemization word or partial racemization, because we already covered this in the previous class. There is a formation of partial racemic mixture, or you can say partial racemization, and this side inversion of configuration. Okay. So first of all, this is all for the like basic difference, like theory wise you can say. Let's see some more difference by some examples there. So let's see some more example about this. So there's a first example. If I'm having carbon, and let's say this is CH2 and CH3. Okay, this side I'm having some CH3, and let's say this is hydrogen and this is bromine. This is present at the wedge position like this, and in this case basically you have to add the water. So should I to go with the SN1 mechanism or SN2 mechanism? Yes, please. SN1, SN2. Okay, wait. Okay, let's just use one more point. If I'm using OH negative, okay, maybe you don't know. So let me tell you one more difference between SN1 and SN2 mechanism. In SN2 mechanism, we are requiring a very strong nucleophile. Okay, very strong nucleophile. Now the question be like, why it's a very strong nucleophile? Because think about it. If this is carbon, our living group be like, I'm not going to live. Okay, nucleophile be like, no carbon, leave the living group because I'm a strong one, stronger one. You know, if you want to kick down something, so you're requiring a very stronger one. So what does the term and condition apply? That it's a single step reaction. There is a no positive charge like SN1. In SN1, it is okay because there is already the positively charged carbon, and nucleophile is going to attack quickly because you know the rule, unlike charges attract each other. But in this case the problem is what, no charge, then how the nucleophile is going to attack? The only condition apply here that nucleophile have to be strong in nature so that it can leave the living group there or kick out the living group there. Okay, then now in the chemistry, the very strongest nucleophile is what, you know, if we are using this word nucleophile, so nucleophile, remember in the previous two, in very first, I guess, one first and second session, we discuss about that nucleophile is a thing which one has a negative charge or a lone pair. So remember we discuss about if I'm having a OH has a negative charge or water, can you just tell me between both the cases which one is a stronger nucleophile, A or B? Yes, please. You know the donor one. A, of course. The charge is the reason of the sorrow. So which one has a negative charge that wants to want neutralize first? So it means OH is a very good nucleophile. Yes, definitely OH is a very good nucleophile. But listen, it's a very good point about the case here. Do you know nucleophile? OH is a good nucleophile. But if we are comparing between the living group, so please be noted, water is a very good living group. Did you notice any time in the organic chemistry, if let's suppose I'm having some OHs there and some H positive there. First of all, this one attack here, and then there is a formation of water. Why? Because it's going to be a very good living group. So be noted, nucleophile, stronger nucleophile is the OH, but living group, water is a very good living group. Okay then. So let's just back here. Now the same question for you. This is condition number in condition number B. So according to you, A follow the SN1 mechanism or SN2 mechanism? Because for the SN1 we are requiring a strong base, and for the SN2 mechanism, for SN2 mechanism we are requiring a strong base, and for the SN1 we are requiring not very much strong base. So what do you think about A or B? One student already answered the question. So there is a two Aditya in your class, right? Okay. So one is SN1 and one is SN2, right? S1 and SN2. Okay, very good. Now I guess you're getting my point. It's easy, right? So it is going to follow that SN1 mechanism. It is going to follow the SN2 mechanism. What is the reason behind this? Very simple. Because this is my weak nucleophile. Okay, it's a weak nucleophile. On the other hand, this is my strong nucleophile. Okay then. So then what is happening there? The next thing is going to be, this is my carbon, this is my CH2 and CH3, and let's say this is CH3 only, and the condition change now. So what is happening there? That this time the hydrogen at the wedge position and this bromine at the, sorry, that OH at the wedge position. Okay, if you to observe this, let me just highlight this bromine dash position, but now OH is the wedge. Inversion of configuration take place. Okay, so it means if you are moving from there to there, so what is happening there? Inversion of configuration take place. So what is inversion? Inversion of configuration. Okay. Okay, so that's it. This is all for the inversion of configuration there. Now let's just move further. How about this case? So in this case, now there's an option for you. We're getting racemic mixture or what? Yes or no? We are going to get a kind of racemic mixture. In the previous class, we discussed about the mechanism, if you remember. Obvious, yes, right? Because it's a SN1 mechanism. So there's a two possibility. That is a possibility number one. If you're having a carbon, okay, maybe the hydrogen will remain same, and this OH is going to connect here, OH. And this is some CH3 group, or plus maybe that is the condition be like this is my hydrogen and this OH be like this. And see, listen, racemic mixture may or may not be there. 100% racemization need not be there. Okay, there we are having a partial racemization. Okay, partial racemization. We already covered this point in the previous class. What is the meaning of partial racemization? Okay, when we are not having R and S 50-50 there. Okay, let's suppose R is maximum, let's suppose S is maximum. Okay, not 50-50 chances there. So that's it. This is all for the comparison between them. Now your turn. Any problem, any issue in the SN1 and SN2 mechanism still left, please let me know. Yes, please. Any problem? If not, then let's solve some questions only. Okay. Difference. Okay. Wait, I will. Okay. This is the first slide, and this is the second. First of all, noted this, and this is the second slide. Okay. If something is not visible, please let me know. Okay. Okay. Let's see the next mechanism. That is going to be the. This is all for SN1 and SN2 mechanism. Okay. Let's see a question quickly, and then we are going to start with this question. Okay. First of all, please make a note. It is very important for you. What about the knot here? That is in benzylic. Okay. I guess you know the meaning of this word. That is benzylic. So in benzylic and alkyl halide. In benzylic and alkyl halide, there's a knot for you. That is the first point. These may undergo. Okay. If you're not getting my point, wait for a while. I will tell you what I'm explaining here. Okay. Observe this point here. We compare, that is a condition number one, condition number two. This is the only case where both possibility can be there. Why? Because the positive charge is also stable, and even the crowdiness is not that much there. Okay, so that's it. This is the meaning here, that these may undergo both kind of mechanism. So you can say these may undergo both. This can be SN1 mechanism, or this can be SN2 mechanism. Okay, but on the other hand, I'm sorry, I right. It's going to be the allyl. Okay, allyl. I said allyl. Okay, I hope you know the meaning of allyl halide now, because we already covered this point in the previous classes, that if let's suppose we are having a double bond and like this kind of halide, okay, it means you have to count three carbon, carbon number one, carbon number two, and carbon number three. So it's a allyl halide. Okay, and benzylic means that if you are having some benzene, okay, and it is connected with, this is some CH2, let's say this is benzylic halide, it means you can say the carbon connected with this carbon. Okay, let me just give you a kind of brief of the 11th class if you don't know. If let's suppose this is my benzene, if it is connected with this two hydrogen like this, okay, maybe some XYZ, let's suppose X can be connected. This is known as a benzyl. This kind of thing is known as a benzyl. It's benzyl. Okay, and if let's suppose this is my benzene and this carbon is connected with one hydrogen only. Okay, maybe other can be the substituent. Okay, any xyz can be there, any substituent can be there. Okay, so it is going to be the benzyl. Okay, it's benzyl. Okay, next is going to be the, if let's suppose I'm having some kind of benzene and it is connected with the carbon, all three are substituent. It's going to be the benzo. You want to justification, so let me just give you a kind of example. Okay, so what is the meaning of this? If let's say this is connected, you know the meaning of this is going to be the benzyl chloride. It's going to be the benzyl chloride. What is the meaning of this? This given hydrogen, this hydrogen basically connected with two hydrogen here. So that's why the name is what? Benzyl chloride. But on the other hand, if let's just suppose if you to observe this point here, you know the meaning of this word. Can you just tell me the name for this? Okay, Payal. Okay, sorry. Okay, Payal, you can leave. Benzaldehyde, right? So have you ever noted you are using benzyl? Why the L is there? Because C, because one is the hydrogen. So that's why the name for this compound is going to be the benzaldehyde. Don't say ma'am, but aldehyde. No, no, no. It's what? It's really the benzaldehyde. And one more, the last one. What is the name of this? You know the name for this one at what? Benzoic acid. So did you notice something? Benzo have to be used there. So it's a benzoic acid. So that's it. This is how you have to give the name of the compound there. Okay, I hope this point is clear for you. So let me just back here. So in allyl one and in benzyl one, both can be there. But what if? What if let's suppose we are having the vinyl halide? If you are having a vinyl halide, so basically, in case of vinyl halide, okay, first question for you, that is what is vinyl halide? Carbon, double bond, and some halogen is connected. So do you know it is not going to follow SN1 mechanism, not even SN2 mechanism. If you remember, I asked a question to you earlier that if let's suppose I'm having a benzene and there is a some halogen, is it really possible to replace this halogen with some OH group? Then your answer be like no. Why? Because a partial double bond character, and just because of the sp2 hybridization it is very difficult to break the bond. Hence, what is the conclusion here? Let me just back here, that only in allyl or benzyl the SMO and SN2 mechanism is possible, but not in vinyl halide. Okay, that's it. This is all for the mechanism. Let's see the third type of mechanism. This is only for the aromatic system. Okay, so the third mechanism is going to be the that SNAr mechanism. Okay, it's a SNAr mechanism. So same as for substitution and for nucleophilic, A for aromatic. So this time we are going to deal with the aromatic systems. For example, if let's suppose a kind of example, if let's suppose I'm having a halogen. Okay, this is the halogen. So in the previous class, remember, we discussed about the point, this is not going to give any direct nucleophilic substitution reaction. If let's suppose there is some kind of nucleophile there, so it is technically not possible for this chlorine to give you the mechanism or the substitution reaction there. The reason is very simple. Yes, Aditya, you're right. Okay. So the reason is very simple there. What we're observing in the previous class there, just because of that there is some partial double bond character there. Nucleophile, and in this case chlorine lone pair, this is attacking here, and there is a partial double bond. This is sp2 hybridized carbon and easy difficult to break. Okay. Then how the SN1 is going to follow the substitution reaction then? Okay. So let's discuss about the condition for the substitution. Okay, so how about the condition of substitution? Condition of substitution in aromatic system. Or let's just talk about benzene because strictly we're talking about the benzene, right? So in benzene system, be noted if I'm mentioning this is benzene, so it is going to be the aromatic point only, okay? So there is a term and condition apply. The condition number one, if benzene, okay? The condition number one, that is if the benzene, or let's just use the aromatic system. Okay, if aromatic system connect with electron withdrawing group. Okay, yes, it can participate. What is the meaning of this? For example, if let's suppose this is chlorine, right? This is chlorine. You know what is nucleophile? Nucleophile is a donor. It's a donor. So nucleophile be like, I want to take chlorine. Be like, no, 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 we can't allow you. But what if you to connect the same benzene with some electron withdrawing group? So now, nucleophile be like, benzene, you want something? Benzene be like, yeah, you can do because right now I'm connecting with the electron withdrawing group. So what is the problem with the electron withdrawing group? If it is connected with the electron withdrawing group, it start pulling the electron density toward itself. It means now our benzene is electron deficient. So did you notice something here? We are forcing the benzene that you have to do the reaction. Okay, so the condition number one, yes, there is a condition number one. Okay, then. So let's just move here. Now, the next question for you. There's a three options for you. If let's suppose this is my chlorine, NO2 group connected here. This is my chlorine, NO2 group connected here. And this is chlorine, NO2 group connected here. Can you just arrange them in order of nucleophilic substitution reaction, please? My question to you, arrange them, arrange in order of nucleophilic substitution reaction. Okay? Yes, please. CAB. Okay. CBA. CAB. Okay. So remember one point we discussed already so many times, that if we are checking for the plus M or minus M effect, right? That if you have to check it for the plus M or plus M or minus M effect, it is ortho and para-directing. But don't say, ma'am, but in the previous classes we discussed about that, isn't it my minus M is going to be the meta-directing, right? And if we are having a plus M, it is going to be the para-directing or ortho-directing, right? Yes, we know this thing here. So now my question to you, what is this? Which kind of order this is? Here we're dealing with that basically the ortho mechanism. Sorry. Here we're following the nucleophilic substitution reaction. So yes, please, what we are going to follow here. Substitution and ortho. Okay, let me just tell you very simple thing. Let's just quickly draw the resonating structure for this one, right? So how about the resonating structure here? This is the chlorine. This one has a lone pair. Okay. So if lone pair attack here, this bond open up. Okay, like this. So how about the next structure? This is my benzene. There we are having a negative charge, double bond, and this is chlorine. If let's say some NO2 group connected here, okay? If let's suppose some NO2 group is connected here like this, so what is happening? This negative charge is stabilized by this. You know, that is the mesomeric effect is only present at ortho and para position. Condition number one. Okay. Let's just move further. How about the next step there? If next step is going to be, this is how it's moving, that you can say double bond and chlorine. What if the negative charge here? So obviously again it is stabilized by one more NO2 group if it is connected here, right? So let's see how that this won't move here, and like this. Again resonance is there. But on the other hand, if let's suppose that the NO2 group present at this position, this is my chlorine, okay? NO2 group is present here. Same here, that if you opt to observe here, negative charge here or negative charge here. But at meta position, there is a no negative charge. If there is a no negative charge at a meta position, then what? NO2 group basically not behaving like a stabilizing group or a minus M group at this position. Okay, it's a 11th class topic. We already know. Let me just give you a kind of brief. If this is my benzene, if this is my benzene, there is some Z group is connected. So if you to consider the ortho position, so at ortho position, inductive effect, hyperconjugation, mesomeric, all three effect is there. I'm repeating. At the ortho position, inductive can be there, hyperconjugation can be there, mesomeric can be there. But on the other hand, if we are comparing the meta position, so you know inductive effect is a distance dependent. Okay, I can be there. Hyperconjugation, no. Mesomeric, no. Only inductive effect. I only inductive effect there. But on the other hand, if you have to compare the para position, para one, so para only mesomeric. Only M and H have to be there, because we know inductive is a distance dependent. If you're moving from there to there, so inductive effect start weaken and hence no inductive effect. So at ortho position, all three effect. At meta position, only inductive. At para position, hyperconjugation, mesomeric only. Okay, so let's just back here. Now let's try to find out the answer for this question. That here, if you have to consider this NO2, okay, so for this one we are having a minus I and minus M, both can be there, right? But okay, look at this. In this case, that is minus I only, okay, and in this case, that is minus M only. So if you tops the condition number one, the group, the substituent number A there. So what is happening in the substituent number A? They're both are the stabilizing one. You know, both are the withdrawing one. So it means you can say A is more electron deficient. It A is going to react first. Yes. Then C. Why C? Because we know the rule. We know that A Harry rule, that our mesomeric effect is dominating with the hyperconjugation, is dominating with the inductive effect for everyone except halogen. So first of all, we are getting A, and it is followed by C and then B. So this is the correct answer for this question. That's it. This is how we are going to solve these kind of question. Yes, these kind of question is also important from this chapter. Okay, so the correct answer is going to be the what? That is A, C, and B. Okay, so let me just check. Anyone give you this kind of answer? A, C, B, A, C, B, C, B, A. Okay. I hope you're getting now Aditya and Sri. Yes, please. Oh, I'm sorry. Not Aditya. Richard and Aditya. Okay, this is going to be the correct answer. This is how we have to follow the order here. Okay, I guess you're getting now. So this is all for the SN AR mechanism there. Wait for a while. Okay, I'm sorry. So let's continue further. Now let's discuss the mechanism behind this. Okay, so it is a one of the famous one. It's known as a mechanism. I said mechanism of SNAr is there. It is a addition elimination mechanism. It is a addition and then elimination mechanism. Okay. My first question to you, for example, if let's suppose this is my benzene, okay, fluorine group is connected, and this is my NO2 group. Second one, let's suppose that bromine is there and this is my NO2 group. Third condition, let's suppose this is benzene and this is chlorine and NO2 group. And the last one, that is this is iodine and NO2 group. Can you just tell me what is the rate of the nucleophilic substitution reaction there? Chlorine, bromine. This is A, this is B, this is C, this is D. Now all four are at the like NO2 has a para position. So which one you to follow? According to you, fluorine, chlorine, iodine, bromine. What should be the order? If I'm observing something, only nucleophile, only living group is different, right? So follow the nucleophilic order. That is living group order. Iodine, bromine, chlorine, fluorine. Who is going to react first here? Am I audible and visible? Because no one is responding. Yes, please. Hmm? Okay. So I'm assuming your answer have to be, ma'am, it is going to be the D because the iodine is a very good, you can say living group, then bromine, then chlorine, and then fluorine, right? So this is the correct order here, right?
Okay.
Okay. So about the order there, that is you can say D is going to be the correct answer, then C and then B and then A, right? We are assuming this. But let's follow the mechanism because mechanism play a very much important role. This is a one of the famous addition elimination mechanism. It is known as a addition elimination mechanism. It means first of all thing is going to be added, yes, then eliminate, yes. So for example, if let's say the condition number is what, that this is my benzene particularly, there is a some electron withdrawing group connected, let's say. Okay, this is some living group, it's obvious. And now what is going to happen in this case? This is nucleophile first attack, nucleophile first attack. This is how the bond open up, and what we are getting, that there is a negative charge, double bond, and this is some electron withdrawing group, and this is some halogen, and plus now the nucleophile is also attack here. Okay, nucleophile plus halogen both attack here. Okay then. Now that if you to observe this negative charge start moving, this move from there to there, there to there, and what is the next kind of thing? Double bond negatively charged. This is some electron withdrawing group connected here, and still halogen and nucleophile is connected here. How about the next step there? This one is moving there, and double negatively charged, and still this is nucleophile and halogen, it's electron withdrawing group. In all three cases, if let's suppose I can write that this step, why not I can write this is be like there is a negative charge moving, right? That is negative charge is revolving in this one. This is some electron withdrawing group, and nucleophile and halogen is there, right? This is basically happening. So nucleophile attack, negative charge start moving, and resonance stabilize. This is condition number one. The step number one, you can say it's a addition step. The step number one is the addition step. So it's known as a addition elimination. First one is addition. Now, second step is what? You can say that is elimination reaction. Sorry, elimination step. So how about the elimination step is there? Now, this negative charge is basically stabilized. There is some electron withdrawing group. And now this is nucleophile and this is halogen. Okay. So halogen leave. Okay. And what we are getting finally, that is we are getting only nucleophile group is connected here. So this is how about the mechanism. First of all, addition, then elimination. And do you know, in this case, in this case, this is the RDS step, redetermining step. Okay. This is a rate determining step. So it means in this case was not going to vary the reaction, the leave of the halogen, or you can say the living of the living group there. So maybe this question came, ma'am, you said that living group is not that the step, the last step when the living group leave the molecule is not the rate determining step, it's a fast step. It's not a rate determining step, but why you are saying then iodine first, then chlorine, then bromine, and then fluorine? No, it's wrong. It's not correct. Cross this. It's wrong. It's completely wrong. But question be like, why it is wrong? What is the reason behind this is a wrong there? Okay, if you have to compare between the rate of fluorine and chlorine, let me just tell you a very simple point here. If let's suppose this is fluorine group is connected and this is some nucleophile, this is a RDS step. The first step is the RDS step there. Okay, and this negative charge is like revolving. Condition number one. Condition number two, still this is my benzene and this negative charge is revolving like this, and this side we are having chlorine and nucleophile. If you to observe, this is a common thing. This is a common thing in both the cases. What is the new here? Here you are having a fluorine and here you are having a chlorine. Can you just tell me who is going to stabilize negative charge more? Okay, yes, in both the cases resonance, yes, in both the cases everything. But who is going to stabilize negative charge more? Is it like a fluorine or a chlorine? Think about it. You know the phone of the dawn of the periodic table, right? Fluorine is the more electronegative. So fluorine be like, don't worry, I can handle the negative charge. Okay? So it means this is a very good minus I group as compared to the chlorine. So that's why this is more stabilized over the chlorine, and hence in this case the rate of reaction is fast when we have to follow the addition elimination reaction. Okay, so this is all for the SNAr mechanism. It's a two-step reaction, addition step and elimination step. That's it. And in this case, the rate of the fluorine is more over the chlorine there. Okay, that's it. This is all for the today's class. And okay, done from my side. Any problem, any issue you're facing in today's class, please ask now. Okay, this is all for over for the reaction coordinate. Sorry, reaction mechanism. In the next class, we will continue with our haloalkane and haloarine chapter. Yes, please. Any problem? Okay then. So let's end the class then, okay? So thank you so much then everyone for joining the class. Thank you so much.